So corrosion can be either an acidic or, when we talk about corrosion can either be acidic corrosions or alkaline corrosions, okay? And I'm going to talk about acidic corrosions first, okay? So when we talk about acidic corrosions, okay, we're talking about H2 evolution. Okay. So for example, okay, you have iron that's exposed to water, right? And plus 2H plus goes to Fe2 plus H2. Okay? So this is what happens, okay, when hydrogen evolution occurs as a part of the corrosion process. And so, so this is the overall reaction. I should write this first. So Fe plus Fe goes to Fe2 plus 2 electrons. Okay. So this is the anodic reaction. This is the cathodic reaction. Okay. So 2H plus in solution, okay, aqueous, plus 2 electrons goes to H2 gas. Okay? And the overall reactions. Overall reactions is, okay, Fe plus 2H plus goes to Fe2 plus. Okay? So this is overall reactions. So this is an example of the acidic corrosions of iron. Okay? So corrosions of iron can happen in alkaline conditions as well. Okay? But the product is different. Okay? So alkaline corrosions. This is the oxidation of iron. So we have the anodic reactions. Fe plus 2OH minus goes to FeOH. So because we're in the pH greater than A, right? pH is greater than A, yeah? There's more hydroxides over here. Okay? So H plus times OH minus is equal to 1 times 10 to the minus 40. So you can use this to recalculate the concentration of OH minus. But anyway, they should add up to 1. Okay? The concentration H plus concentration OH minus in 1 liter of solution should add up to 1 mole, okay? At the most. So at pH greater than 8, we're in an alkaline environment, so there's a lot more hydroxides, right? Whereas contrary to the acidic environment, there's a lot more H plus protons in solution in the acidic pH. Okay? So because there's more hydroxides in solution, the ions react with the hydroxide according to this reaction, okay? And so this is symbiotic reactions, and the prothonic reactions that associate with this is the oxygen reactions with water, okay? So electrons to form hydroxides solution, okay? And the overall reactions is O2 plus H2O. Oh, I'm sorry. 2Fe plus O2 plus 2H2O goes to 2FeOH2. And so this is the overall reactions, okay? And this iron hydroxide, right? The iron hydroxide in solution continues reacts 4Fe OH 2 plus O2 plus 2H2O goes to 4Fe OH. So this is a typical corrosion process for metal, okay? Because we work with iron, stainless steel, okay? Components, the largest components in stainless steels that we work with in everyday life is iron, okay? Other metals have similar corrosion like reactions, okay? But I'm not going to go over those, but this is the same example, okay? So this is metal. Corrosion of metal, okay? So we're going to talk about corrosions of carbon. So this is corrosion of metal, right? common material types that we work with. Okay? So, so what we need to know is that carbon is stable and acid. Okay? Okay, it's mostly stable and acid. Okay? So it doesn't react with hydrogen chloride and hydrogen sulfuric acid. Okay? So corrosion in this acid is minimal. Okay? Carbon corrosion in metal, in acid it's not very much. Okay? But corrosion in alkaline or base, I should say base. Okay? Corrosion in base is more severe. So carbon is oxidized. Okay. To CO2. Okay. So in the following reactions. So this is the enotic reactions. Carbon plus H2O goes to CO2 plus 4H plus 4 electrons. And the cathodic reaction is O2 plus 4H plus 4 electrons goes to 2H2O. So this is oxidation of carbon, right? To produce carbon dioxide, okay? And this is the reduction of oxygen, okay? To form water. Okay? So the overall reaction is this. So carbon plus oxygen goes to CO2. Okay? So we talked about corrosion to metal, okay? And we talked about corrosion of carbon, okay? And we're going to talk about chloride corrosion, okay? So, chloride. So this type of corrosion, right? This is a chloride corrosion is caused so So chlorides, okay, has the following characteristic, right? Is small, right? Is reactive, right? And it has a tendency to absorb weak points. Weak points. So, defects, etc. Breaks in defects, breaks in passive forms. And he has a tendency to break. Breaks, okay. He has a tendency to breaks in breaks oxide. Okay. So for example, we have fluoride in solution, right? Okay. So over time, you have a piece of metal, okay, and you have a passive film. So this is metal. This is metal oxide. So chloride gets to the surface, and you'll attack this. And so it causes a break, okay? So expose the metal underneath, and chloride goes in, okay? And H plus goes in, these reactions. Okay? So chlorides attach the surface, cause breaks in passivation, and then H plus movement to react with the underlying metal, and and more chlorine movement to balance the charge, right? This is hydrogen concentrates and tips. Okay. Acid corrosion increase. Okay. Pit deepens. More chloride movement, more H plus movement, pit becomes larger. Something like that. Okay? So this is the pit acid. So these steps here, 1, 2. So this step here is like pit acidification. Pit becomes acidized. Okay. So this is the methods for chloride corrosion. Okay. And as more H plus movement, right? Chloride movement to balance the charge, right? Because hydrogen is H plus, it has a positive charge, and chloride is a minus charge. So as the charge, the pit becomes more negatively charged. Okay, the H plus, as the pit becomes more positively charged because it has a lot of protons, the chloride movement balance the charge, and so this reactions accelerates. Okay, so basically chloride corrosion, right, is passive film breakage followed by acid corrosion. Okay? Now, so these are the basic